Let's talk about the law of Demeter. The law of Demeter is a design rule that tries to help you to reduce coupling in your systems. Remember, Object Orientation 101, coupling is bad, cohesion is good. Cohesion is how much certain pieces belong together and how much they make sense. Coupling is how much you're intermingling, coupling two pieces to each other and making them difficult to separate from each other. So again, coupling bad, cohesion good. The law of Demeter is a design principle that tries to help you minimize coupling in your systems. So what does the law of Demeter say? The law of Demeter says that it's okay to talk to A, it's okay to call A dot B, but it's not okay to call A dot B dot C. So what do we mean with all these random letters, right? Assume you're in a method, then in the method, it's okay to access something that's in your scope, i.e. A. And also, it's okay to access a public member on A. So it's okay to call B on A, right? In the context you're in, it's okay to take A and then call a method on it, B. Or more generally, access something on it, i.e. B. But the law of Demeter says that it's okay to go that far, but not further. So you can't take A, call B on it, and then call C on B. The reason for this, again, is to reduce coupling, because what you are doing is that you're coupling to the fact that A has B and that B has C. So you're coupling to the whole chain instead of just coupling to A or just coupling to B. But this is of course getting super confusing with all the letters. So let's talk about an actual example. So consider this super silly example. Let's say you have the ocean. So we have a class that is ocean. In the ocean, we have fish. So we have a class that's fish. And in the ocean, we put fish. So in some sense, the ocean is a collection of fish. Assume then that fish, the class fish, has a method that returns a boolean that is true or false, dependent on whether the fish is hungry or not. So let's call that method is hungry. Assume now that whoever has access to the ocean, let's say the program, right? Let's think about the hierarchy again. The program has access to the ocean has access to a bunch of fish instances, and each fish has a method that returns a boolean, is hungry, and determines whether the fish is hungry, the particular fish is hungry or not. Assume that the requirement is this. Assume that what we want is that we want, from the program's perspective, to gather out all of the fishes that are actually hungry. So more concretely, what we want to do is that we want to access the ocean, we want to access the collection of fishes, and then we want to filter out all of the fishes that are hungry. So how would we do that? Without thinking about the law of Demeter, what we would probably do is that we would say, okay, ocean, let's say we have an instance of ocean, we say ocean dot fish, right? In plural, as in fishes, right? And we get a collection of the fish. And then maybe we would use a filter function, right? We would run filter on the fish and then give it a function that we use as a filter. And this filter would call is hungry on each of the fish. That would, in essence, give us only the fish that are hungry. What's the problem? The problem then is that we are breaking the law of Demeter. Or actually, it could be called Demeter. I'm not actually sure what the word is, but who cares? So let's generalize back to letters. The ocean is A. The fish is B. And is hungry is C. So essentially, what we're doing when we're performing this filter is that we're calling C on B on A. But with some slight nuances because we're doing collections and we're doing filters, etc. And that's it. So the law of Demeter says, don't do that. Instead, we should create some kind of facade, some kind of adapter that delegates from B to C. We should create a method in B that does the thing correspondingly to why we want to call C. So in this particular case, what should we do instead? In this particular scenario, the idea is that we should take a And instead of grabbing out, instead of extracting the collection of fish, we could just say, get all hungry fish, or something like this, right? Or just hungry fish, get all hungry fish. In other words, when we have the ocean, we have one method that we call, and that method itself is responsible for determining which fish are hungry and which fish are not hungry, and then returning those. So instead of B in the program, calling A, and then calling B, and then calling C, we're simply calling B on A. And in this case, B were not the fish, but the method get all hungry fish. So that's it. Let's wrap this up. Remember, coupling the design of one object to the design of another object is a bad idea. Coupling one object to the design of another object, which will give you another object, is even a worse idea. So coupling to chains is even a worse idea than just coupling between two objects. And to identify such coupling chains, we use the law of Dependency to realize that we have such a coupling chain. And essentially the way we get rid of them is simply by creating a method that delegates to the thing that we want to call, instead of exposing the actual thing that we want to call. Which generally, if you think about it, is a very good idea. Because it's information hiding. We're hiding the details of something that the outside should not necessarily have to be caring about. So that's it, I'll stop rambling now. The law of Dependency, it's okay to say A, it's okay to say A dot B, but it's not okay to say A dot B dot C. If you have questions or angry comments, please shoot them in comments and I would love to discuss with you. Beyond that, be sure to subscribe because there's more of this coming always. Let's talk about programming. Probably heard the expression code should read like well-written prose. In other words, that your code should read kind of like a book. That your code should be as easy to understand as literature. That might seem completely unreasonable, so let's actually talk about what that means and how we can achieve that. So if you read the book Refactoring by Martin Fowler, you'll come across a bunch of different patterns, and the way I understand it, a lot of these patterns are intended to make your code read like prose. They're intended to, yes, increase the flexibility of your design, but also to make your code more human readable. So let's talk about a quick, very simple example. Assume you have an employee class, and assume that employee class has a method called calculate salary. And assume that there's some kind of complex and nasty logic going into this method. So whenever you call the calculate salary method, it touches a bunch of things here and there, and eventually you will get a number out of it which represents the monthly salary. So this is a particularly obvious example. When you have a nasty piece of logic like this, when you start to really dig into it, and I highly recommend the book Refactoring by Martin Fowler, I'll link it in the description, because that book gives you a bunch of atomic steps that you can take to carefully refactor your code without significantly breaking your system. I'm sure we've all been in that position where we have a fantastic idea of how we want to refactor our system, and then we begin, and then we find ourselves with a broken system for 2 weeks. The refactor book, in other words, gives us a bunch of techniques that we can use to avoid ending up with a broken system in 2 weeks. So, going back to the example of the calculate salary method. So assume that you start to dig into this method and try to pull out all of the different pieces in order to understand it. So we'll start by just making comments. When you start to separate the pieces of the method, you may start to realize that in this particular scenario, what actually happened was that we first got the employee's base salary, in other words, the sort of baseline salary for that particular employee. After that, we added the bonus of this particular employee. And then after that, we added on the employee's commission. So in other words, this may be from a system where you have a bunch of salespeople, and the salespeople are working with a base salary, a bonus, and a commission. Right? So we have these three pieces then. And what you need to ask yourself then, when you find yourself in one of these situations, is that, okay, actually I have three separate pieces. And instead of just pushing them all into one method, I separate these pieces into, or I sort of elevate these pieces or promote these pieces, and at least make their own methods. Potentially public, maybe private, but at least their own methods. And instead of then incorporating the logic in this method here, we simply call those methods instead, and by doing that, we can design the name of the method, which means we can make our code read like prose. Let me show you how. So when we pull out these pieces into blocks, right, blocks that we've commented, it's actually a very easy exercise to just pull these out into separate methods. We'll pull these out like so. And when you have these as separate methods, you will realize that depending on the names of the methods, your code suddenly starts to be like prose. If we now read what the calculate salary method does, let me read the whole method. So, calculate salary is a method that returns an int. There's no argument. And when it's called, what it does is that it says return, calls calculate base salary, calculate bonus, and calculate provision. So suddenly we can start to reason about this code as if it were text. Before, when a programmer who didn't write this method, or consider yourself in 2 months revisiting the code, that person looking at this piece of code would now be able to actually understand what the method does roughly without having to sort of dig into the internals of the method. Whereas before, that person had to dig through procedural code and try to understand what a procedural code actually meant. There's a massive gap between what it does and what it's supposed to mean. Be aware that we're only scratching the surface of this. You can really push the idea of making your code read like prose to a very far extent. If we generalize, the idea is simply this, that instead of exposing the details, we encapsulate the details somewhere and then push the details downwards into methods, into classes, down into the system, where supposedly another programmer or ourselves in 3 months won't have to understand those things, because the thing that number of lines that they perform are so good and few and has such a good name that we can trust and understand what it does, and then we simply just call it instead. So whenever you see a lot of code in the same place, be sure to ask yourself whether you can actually extract these pieces and make your code instead read like prose. And if you have a colleague who fancies very long methods, please give him or her this video so we can debate in the comments. That's all for today. Thank you very much. Be sure to subscribe so you won't miss the next video. See you later. Let's talk about the difference between proxy pattern, adapter pattern, and the block pattern. Oftentimes, one of them are explained in terms of the others, and also oftentimes the lines simply blur between them. So the other day I had a discussion with someone about proxy pattern, and I sort of loosely use the terms facade and adapter in that conversation, essentially referring to the same concept. So traditionally, I haven't really been separating these concepts in discussion, but this piqued my interest. I did a quick search and I found this article. I linked the article below, by the way, and I just figured it had a really good explanation of the differences between these. And before we dig any further, I would like to say that, of course, the way I see it, regardless of whether you're using the word adapter or facade or proxy, I think when people look at your code, they will understand what you mean, and when you say one of these terms, they will understand what you mean, essentially. But the way I read this article that I keep mentioning, they seem to say the benefit you gain of using the correct term is that people will know which scenario you are referring to. So in other words, there are detailed differences, there are nuances between these two patterns and the cases in which you may want to use them. So using the correct word would help a person who understands these nuances to understand what scenario you are specifically talking about, and in some sense then understand what problem you are solving. Okay, last point before we dig into the patterns. If you are not familiar with any of the patterns, let me just quickly say that essentially what all of these do is that you have a place where you want to call a method on an object, but instead of calling the method on the object, you call a method on some other object who delegates to that first mentioned object. Essentially, that's sort of the core of both facade and proxy and adapter. But the nuance lies in why you want to do this and how you do it. But with that out of the way, let's get down to what these actually mean. So again, we have proxy, adapter, and facade. So, proxy pattern changes the implementation, but does not change the interface. Adapter pattern changes the interface, but does not change the implementation. Facade pattern essentially does what the adapter pattern does, but has some more nuance to it. The nuance being that facades usually grow large, and a facade indicates that there's something wrong with, or that there's a problem with, the object being facaded. We'll dig in more in detail in a moment, but let's just recap. So proxy changes the implementation without changing the interface. This means that you can replace a proxy with the original object and vice versa, because the interface is the same. The name of the method are the same. So if you have some kind of list class, and on this list you have the methods push and pop, and if we then create a proxy for this list, then the interface needs to be the same. In other words, the proxy needs to always also be able to respond to push and pop, but it may do different things. So for example, of course the usual implementation of a pop is that you get the element back and that the last item in the list or array or whatever is popped off the list or the stack or whatever it is. But so say that we, for some reason, our proxy for some reason doesn't actually want this behavior. Our proxy wants the item that you want to stay inside of the list. So in this case, we could create a proxy that has the method pop. Whenever you call the method pop, it doesn't just call pop on the proxy object. It calls pop, but then it also pushes back the object that is pop. So in other words, we manage to get the item back, but we also keep the item in the list. Right? So in other words, this is changing the implementation. We have the same interface, so we can exchange proxy lists for normal lists and use them interchangeably in the application, but the implementation has changed because the proxy object does something else. Moving on to adapters. Adapters change the interface, but does not change the implementation. So if you think about, I think the best analogy is probably to think about power adapters, right? When you travel to a new country and you need a new power adapter, it's not that you don't want electricity. I mean, you want electricity. You just want to be able to plug it with a different interface. right? You want to be able to plug it using a different connector, right? And the same thing is true here in code. So you want to call push and pop, say, but in your application, you may have, in many places, assume that you had an object that responded to, say, get and set. Disregarding the fact that the interface I showed was highly confusing and get set sort of implies that there's only one item that you can get and set and not list. But disregarding that, I think you get the point still. The adapter in this case does not change the behavior of the adapted object, but it simply delegates to the adapted object with by changing the message we send that object to whatever is appropriate for that object. But it receives messages using the syntax that using a different interface, using the interface that we've used elsewhere in the application. So again, the adapted list has get set, while the list has push and pop. So the adapted list cannot in the application be exchanged for actual lists because they have different interfaces, right? You can't just take away an adapted list and instead input an actual list because they have different interfaces. However, you are now able to use the list in your application even though you've written your application using a different API, using a different interface, i.e. the get set interface. Alright. Lastly, facades are essentially the same thing as adapters. In other words, they too change the interface but does not change the implementation. But the article argues that facades usually grow large over time, and that the sort of distinction or the nuance lies in the fact that facade over, right? The thing that they are facade over, that they are a facade over, that thing kind of has some issues, or is not necessarily superb design, right? Or should not be considered ready to use, right? For some reason, it will prove to be design. So, in other words, adapter pattern doesn't necessarily, according to this article, as far as I understand, doesn't necessarily communicate to other developers that you are unadvised to use the thing that the adapter is adapting over. The adapter is adapting over a list. That doesn't necessarily insulate to other developers that you should not use the list or the array or whatever we were talking about by itself. In contrast to the facade, which insinuates to developers that one should not use the thing that the facade is a facade over by itself. It may, for example, be legacy, and then can sort of be deprecated. Right? Honestly, I think it's super hard to work. I would, in a real-world scenario, allow myself to create an adapter that is slightly changed behavior. Right? I mean, this depends on how you want to be. I mean, if you have an adapter that holds for how big you want to interpret it, if you have an adapter that holds two methods on the adaptive object, then it could be argued that the adapter is not just adapting, it's actually also changing behavior. So if you want to be really strict, you would have probably to do something like that. You would have an adapter first, and then you would have a proxy that changes behavior. But perhaps this is one of these scenarios where I would sort of weigh the most benefits. Right? Like if it's trivial and people see that you're holding two methods, then yeah, I mean I would call it an adapter and call it against thing. But if it's something that might be long-lived, then it's a very large matter. I really think there might actually be a lot of value separating the proxy concept or the proxy from the adaptive, or the proxy from the facade. To actually make it very clear to people what you are doing and where the program is moving towards. But I've got to stop hanging out in the parking lot now. So, as usual, thank you so much for watching. If you have any comments or questions or angry outrages, right, just hit them down in the comments. And if you have ideas about what you want talk about in future videos, each should be a message. That would be fantastic. And of course, make sure that you not miss the next episode. So, subscribe. More goals. Moving forward. Becoming better. Okay. I want to briefly talk about tell, don't, ask. So the design principle says that you should tell and you should not ask. What does it mean? In this context, asking means checking a property of an object or running a method on an object and then somehow using the information that you get back to make some kind of decision. So you're in a place in your code, you have access to an object, you ask the object something about its internal state, which could be that you check a property of it, or it could be that you run a method and get some kind of value back. You run a function and get some kind of value back. With that information that you've gotten back, then use that as a basis to make some kind of decision. So the classic scenario would be that you use it in an if. Right? You use it in some kind of switch state. So let's be even more precise. This means you have an object, say you have an animal, and you ask animal dog is hungry. Right? You ask the animal whether the animal is hungry, and then you use that information, the pool that you get back, as the information you need to determine whether or not you should feed the animal, for example. So tell and ask essentially says that what we are doing is that we are first asking the object a question and then telling it to do something. But in fact, in many cases, the object in question have enough information about itself to make the decision on sort of its own behalf. So let's be super specific about the scenario. So the code is this. We have an animal class. The animal class has a property, but in this case, we'll view it as a method. So it has a method that is called isHungry, and it returns a bool. So if the animal is hungry, it returns true. If the animal isn't hungry, it returns false. And also the animal has another method called eat. So what we want to achieve here is that we only want to feed, only want to call eat on hungry animals. So we want to first make sure that the animal is hungry when we have an instance, and then we call eat on the animal to make sure that we're feeding hungry animal. So again, if we would be asking and not only telling, then we would first from the outside create an instance of the animal object, ask the animal whether it is hungry, and then if it is hungry, feed that animal. So you might think that the scenario is kind of silly because you would go, but who would write this kind of code? But if you start to think about it, you'll be surprised about how often we sort of spontaneously come up with this kind of code. Right? We're so used to sort of introspecting objects, to asking objects about their internal state so that we can make decisions on their behalf. Of course, the tell don't ask principle in this case says that what we should actually do is not ask the animal about its internal state, but instead we should tell the animal to do the thing that we would want it to do if its state is such that it can perform the action we want it to perform. So if you think about the preconditions of running eat in this particular scenario is that the animal is hungry, right? But to determine whether the animal actually is hungry or not, actually only need information from the animal. We don't need any information from the outside. So consequently, this is an action that could be performed, or this is a decision that could be determined or taken solely within the animal itself. So consequently, what would the other design look like? A design that corresponds to the tell don't ask principle would instead only call eat on the animal instance, and inside animal, the animal would perform the check on itself as to whether it is hungry. Right? This of course assumes that not only is it so that the animal itself can determine whether eat can be called, but we also assume that the animal can handle whatever needs to happen in the case that it does not want to perform the action we ask it to perform. So for example, if from the outside we wanted to do something that's completely non-animal related in case of the animal not being able to eat, then the situation is more complex and it's not as obvious that the logic should move into the animal. But in this case, since we have no path for the scenario where the animal doesn't want to eat, we have no other path of execution if the animal doesn't want to eat. The only thing that we want to not happen is that the animal eats, and we don't actually want anything to happen when the animal doesn't want to eat. So in that case, the animal, the eat method of the animal is simply silently, quotation marks, fail. Of course, it doesn't silently fail, it just silently doesn't do anything, which in this case adheres to the specification. So to recap, tell don't ask essentially says that you should not introspect, you should not ask objects about their internal state in order to make decisions first. Instead, you should let the objects inspect themselves and determine whether they can or cannot perform the action that you asked them to perform. You can even push this further and say that, because previously we stated that if all of the necessary information resides within the animal, you should make the decision within the animal. But even if you have information outside of the animal that you need in the sort of condition where you want to determine whether the thing that you want to run can be run or not, even in that case, you could even still tell to not ask, right? The way you would do that is that you would pass the information that the animal needs to make a decision into the animal. So instead of taking information out of the animal, you pass information into the animal, right? The benefit is not necessarily as obvious here, so we have to dig into more details in order to determine whether there's win here or not. But in the trivial scenario, I would say this is almost always a win. If you think about coupling, for example, if we ask and not tell, then the user of the animal needs to know about the property of the animal, or the function we call get the value, i.e. whether the animal is hungry or not. It couples to that method, but it also couples to the key method, right? But in the scenario where we're telling only and not asking, then we're not coupling we're only coupling to one method. We're only coupling to the eat method. So in terms of coupling is lower in the telling scenario in this case. So that's it for tell on that. This is one of these interesting design principles where it's not always obvious that there's a win in telling instead of asking. So if you have examples of such scenarios, it would be fantastic if you could shoot them out in the comments and we could discuss it. I hope this has been helpful. If you like this video, I'd appreciate it if you hit the like button. And if you want to see more of these code videos, be sure to subscribe. I'll see you next time. I will talk shortly about the concept of premature abstraction, arguing that you should be a bit more careful before calling someone out for performing premature abstraction. The argument often goes something along the lines of that. It's premature because if you're abstracting, that means you have to solve the general problem that might be very difficult, when in fact you don't know that you need to solve the general problem. So instead you should just solve the specific problem. To make the case, I would like to tell you a short story of a system I was involved in many years ago. I've thought about this system time and time again afterwards, and I've sort of come to the following conclusion. So let me tell you what the system was. Or honestly, a tiny portion of the system. So the thing I was asked to develop was a grid that displayed a number of images. Now, that's fairly trivial, but the problem, the crux, was that the number of images were arbitrary. And obviously one of the requirements was that the images should not distort. So you couldn't just stretch the images. Now, if you could stretch the images, the problem would be more trivial. But if you, of course you can stretch them. You have to scale them proportionally, not stretch them like you can't make them 200% wide and 100% in height. Now, there are, of course, general solutions to this problem, and they're not even that complicated. So the one I went with in the end was an idea where you split, actually after discussing with my father about this, I figured the easiest way to approach it is probably to split the canvas in half, and then split one of the halves in half, and then split one of the halves in half, and then keep doing this procedure until you have an equal number of halves in comparison to the number of images they need to display. And that does work. However, of course, this took a longer time than if I would have simply said that actually we need a fixed number of images, or we are okay with the fact that an extra image causes the page to scroll, or if we decided upon whether the page would usually be viewed in landscape or portrait. I didn't mention that when I was talking about the problems before, but one of the things that make the problem more complicated is, of course, that you also want to not have, say, 30 columns in 2 rows, right? That doesn't really display very nicely, and that, of course, depends upon the resolution of the screen you're viewing on, or rather the dimensions of the window. But let's not dwell on either the solution or this particular problem. The point is that there is a solution, but the solution took more time to find, or it took a longer time to find a solution that is more general than if we would have imposed some constraints on the requirements and instead solved the specific problem. So when people say that you are prematurely abstracting, a lot of the times you'll need this argument. They'll say that you are trying to solve the general problem when in fact you should be solving the specific problem. Because, you ain't gonna need it, right? You are not going to need the general solution. In this particular case, it was extremely evident because I, as a developer, spent a lot of time on this particular feature, right? You know how programmers really want to solve some problem that we're facing because it's sort of intrinsically interesting in itself. I found myself in one of these situations, this problem, so I really wanted to actually solve it. So again, oftentimes the argument is that you're trying to solve a general problem when in fact you should be solving a specific problem. Now, the point I want to make now is that you don't always have to solve the general problem, but you could still be creating abstraction. So abstraction in itself does not only mean solving the general problem that you might think is the general problem. It might also, it could potentially mean abstracting in such a way that you allow for yourself to change the specific implementation if your requirements change. So in this particular scenario, instead of trying to solve the display all images when all the pieces are moving, or let's say, without making any tough decisions, instead of trying to solve that general problem, I could solve one of the specific problems, essentially, for example, choosing landscape or portrait. I would have an implementation for that. You could have a different implementation for overflowing, when you have an extra image more than you, or you have, say, uneven quotation marks number of images. These are all specific solutions, and the point is that if you implement one of these specific solutions, but make sure that you abstract your code enough such that you will be able to exchange your specific solution for another specific solution. And if we're being more specific in this discussion, I should perhaps call it a specific algorithm rather than a specific solution. It's not about solving a mathematically tricky general solution. You could still solve just a specific solution, but because you know that the specific solution might not be the right solution, might not be the solution that a customer wants, or be the solution that you will want in the future, then you take heed for that. You say, yeah, actually, we might need a different specific solution in the future. Or sorry, I should start saying algorithm. We might need a different specific algorithm in the future. So we'll create a scene in the system where it's possible to exchange one specific algorithm for another specific algorithm. Essentially, dependency injection. And by the way, if you want to know more about dependency injection, I highly recommend you to check out my other video on dependency injection. So, using this kind of abstraction, I would strongly argue that this is not premature at all. This is completely sensible. This is expecting that you have understood a requirement incorrectly and creating a scene in your system where you in the future will be able to exchange the one specific piece for another specific piece that may take you close towards correctly understanding that particular requirement. I'm running out of battery, so I'll have to wrap this up. But the point is, be careful when you accuse someone of prematurely abstracting. Just because someone is abstracting does not necessarily mean that they're spending time trying to solve the general problem. they could, in fact, be creating a scene that will make it possible for you to exchange one specific algorithm for another specific algorithm in the future. Now, I would argue that performing that or creating that kind of scene is almost effectively free. Of course, it's not free, but the cost of performing it is very, very low. In comparison to, of course, the cost of solving the general problem is, of course, not low. So the criticism of solving the general problem is, of course, warranted. So those are my 5 cents. Be sure to subscribe if you want more code talks like this, and I'll see you next time. If it barks like a duck, it is a duck. This is one of these phrases people tend to throw out and then make everybody else confused. Let's talk about duck typing. So I can't give you the deep down depths of what it theoretically means. We'll talk about that in another video. But generally speaking, duck typing is about determining the suitability of an object based on what it does rather than what it is. To be even more specific, whether a method can be passed a specific object, i.e., whether the object is suitable as an argument for the method, is commonly, or in a non-dynamic language, determined by the type of the object, i.e., what type the object is of, i.e., what it is. But duck typing says, actually, what does it matter what it is? Let's instead determine whether the object is suitable or not based upon what it does, i.e., what method it responds to. So in other words, if a method takes an object and then calls the method quack on that object, then as long as the object responds to the method quack, what does it matter whether it's a human or whether it's a duck? Right? The common example is a human pretending to be a duck but still responding to the quack method. Interesting parallel I find is to consider the Turing test. You know, the test for artificial intelligence. It seems to me that the test is about sidestepping the question of what is human, because it's philosophically difficult. So instead of attempting to answer the question of what is human and what is not, the question is sort of restated, where the experiment is designed in such a way that that question is ignored. So the Turing test seems to provoke the question of that if something behaves human, what does the question of whether it is human or not, what does that question matter? If it behaves human and you can't distinguish it from an actual human, then what is really the question of whether it's human or not? Now, this is of course almost a kind of far-fetched analogy. Really, I find it quite suitable for duck typing. Because duck typing does the same thing. It says, what does it matter what something is? The thing that does matter is how you want to use that object. And if that particular object does in fact respond to all of the methods that you want to call upon it, what does it then matter that it is not stated to be of the type that you expected it to be? So, very practically, what does this mean? This means that in dynamically typed languages, like Ruby or JavaScript or whatever, in these languages, you're not specifying the type of something. So when you're constructing a method, and the method takes an argument, you are not stating explicitly, you're not telling the compiler or the interpreter what that method is expecting, what that method is expecting in terms of the type of the argument. You're simply saying that it wants to receive something, and then you go about calling methods on that thing that it accepts. So that means that when you are receiving that concrete object as an argument, you are expecting it to behave according to some particular specification. Or put more lightly, you are expecting it to respond to a certain set of methods. So from a very pragmatic point of view, we could then say that duck typing is really nothing more than polymorphism, but without the hierarchy. So it's dynamic dispatch without an inheritance hierarchy, or without explicit interfaces. So in other words, in statically typed language, such as C# or Java, I'm now ignoring the keyword dynamic, but basically in a statically typed language such as C# or Java, in order to achieve dynamic dispatch, i.e. call a method on an object whose type is not known at compile time, or I should say whose subtype is not known at compile time. Essentially, you have to either create a common ancestor or construct interface. you have to somehow explicitly tell the compiler that you're expecting something that adheres to a specific specification, right? To a specific interface that responds to a certain set of methods. And then you can treat it as such. So, returning to a classical animal example, right? You would say that your method takes something of type animal, and then you would have children that are subclasses of that parent class animal. So you could have lion and cat and dog. And consequently, that means that the method that takes animals can also take lions or dogs or cats. But returning to the concept of duck typing. So duck typing says that it doesn't matter whether a lion is an animal or whether a cat is an animal. What matters is it responds to the methods that we want it to respond to. So in dynamic languages, you can pass any object anywhere, and if the object does respond to the methods that you do want to call upon it, then that object does pass the duck test. In some sense, that it is a duck because it per se, it responds to the methods that make it a duck. So to push this one step further and think about the practical consequences of duck typing, people argue that you should not perform type checking. Type checking is in many senses considered a code smell. We'll talk about that in a separate video. But assuming that you buy that, that has interesting consequences for duck typing. So because in dynamic languages, you don't know what the type is of things that you are receiving. And it may be, at runtime, it may prove to be of any type. So how to make sure that you are not calling methods on, or that you are not calling quark, for example, when given something that is not a duck. So naively, we often resort to type checking. But the strong followers of duck typing, the way I understand it, would instead argue that you should not check for what something is, but you should check for what something is capable of doing. If you should check at all. But assuming that we need to determine whether we can perform some particular action on some particular object or not, then you should check for that capability, and you should not check for the type, knowing that that type does have that capability. To understand this, let's consider an analogy. If you're familiar with the concept of responsive web design, you've probably already come in contact with this concept of not trying to determine what something is, but instead focusing on what something is capable of doing. So in responsive web design, the idea is that there are so many devices out there. There are cell phones and tablets and computers and tons of different browsers and different versions, and like they're just accumulating as the years go by. So the point is that instead of trying to check in which particular environment your application is running, right? The argument is that that will bring you down a path of madness because there's just so many. So we're just going to have to create more conditional to keep on checking for different types. So the argument is that you instead should be checking for capabilities. So instead of determining whether the environment you're running in is an old browser, for example, because I have some knowledge about what that particular browser does or does not support, you should instead check for the capability of performing the thing that you actually want to perform, and then making a decision based on that. So similarly for duck typing, instead of switching a bunch of types that may or may not hit your application at a particular point of the code, you should instead switch all the things that you are actually intending to use, if you are intending to switch at all. In order to nail this down one last time, the concept of duck typing is to not use information about what something is in order to determine suitability for a particular purpose, but rather to use capability as a way of determining whether it's suitable or not suitable for performing that particular purpose. So let's say that duck typing. If you find my explanation completely and utterly confusing, please do let me know, and we'll dig further into this. And as usual, if you want more programming talks like this, be sure to subscribe.
作者寫到手實物嗰個思路，手實物嗰個 F， 其實個內容係專家，控住係或者講係力定真咋，và làm sạch hiệu quả, tập trung phải ra thôi.
So I did a previous video, on why you should be wary of using the static keyword. Naturally, I am amongst many others that have this opinion, but even though some people find it slightly controversial, and since then I've had a few discussions, it has come to my attention that some argue the need for, or the usefulness of static functions because they argue they move towards a functional style of programming. In other words, the argument is that static functions resemble functional programming. I think this is a fallacy, so let's talk about that. So the argument is that static functions are actually not like functional programming. Let's dig into this. Functional programming has many important concepts. Two of them are that functions are first-class citizens and that the functions are higher order, like higher order functions. So I'm not at all an expert, but the way I understand it, it seems to me that functions are first-class citizens and that functions are higher order are sort of two sides of the same coin. They're sort of the same thing. Higher order functions is a mathematical concept, whereas functions being a first-class citizen is a computer science concept. So concretely, functions as a first-class citizen essentially mean that you can create a variable and create a function and reference the function in the variable and then pass the variable around. Higher order functions, on the other hand, the mathematical side, very simply means that a function can take a function as an argument and or return a function as output from the function, or as a return from the function essentially, which is actually not strange at all. So if you think about the function map, right, where you have a collection and then you map a function over that collection, that's an example of taking a function as an argument. Conversely, if you think about the concept of partial application, if you think about currying, that's an example of returning a function. We won't dig into what these specifically mean, but essentially, if you're familiar with these are examples of taking a function and returning a function. So that's higher order functions. Now, returning back to the topic, the point I wanted to emphasize with the previous video where I argued that you should be wary of using the static keyword is that the problem of using static is that we are coupling to implementations and not to abstractions. Instead of painting this picture as a problem, let's paint this as an opportunity. What we want is that we want runtime substitutability, essentially dynamic dispatch. We want to be able to call a method without knowing which object the method recites. Writing flexible code becomes really tricky otherwise. So such a concept is easily supported if you're in a language where functions are first-class citizens or higher order, because you can construct functions that take functions, which essentially mean that you can exchange the function, i.e. the implementation, at runtime. Static functions, however, does not work this way. Static functions, generally, you can't pass around. So I would even go as far as to say that not only are static functions not like functional programming in style, but actually, I think they're less like functional programming than if you would do classic object orientation. Because in classic object orientation, you have polymorphism, you have interfaces. So if you think about it, if you construct an interface that only has one method, and then you have another method that takes something that implements that interface as an argument, then essentially that's like passing a function. Not really, but almost, right? Because then you have substitutability at runtime, right? You have polymorphism at runtime, which you don't have with static functions. So again, functional programming is fantastic, but the argument against static functions have nothing to do with functional programming. So whenever you find someone arguing that you should move towards static functions because it's more like functional programming, please give them this video. Because there are many good reasons to believe that they're actually not. I hope this helps straighten something down. And if you want more programming talks like this, be sure to subscribe. Subscribe. Functional programming makes it way easier to have parallel execution, to essentially execute parts of your program on different machines, or different processes, or in different threads. So I want to briefly talk about why this works. Parallelizing, I guess. To understand why that is so, we first have to understand what a pure function is. So, stated very simply, a pure function has two rules. The first one is that given the same arguments, the function must always evaluate to, i.e. return the same result. So if you have a function that takes two arguments, and you give it, say, a 1 and a 2, you should always, at any point in time, if you give it those two values, you always get the same value back. Rule number 2 is that it should not have side effects. A side effect essentially stays outside of the function itself. So in other words, this means that your function can, for example, write to disk or write to a database, which, as you might guess, of course, makes it very hard to write a usable program. But that's a topic for a whole other video. So let's talk about that some other time. So when you have a function that follows these two rules, you have a pure function. So the question is then, if you have two functions that are pure, why is that easier to run in parallel than if you would have two impure functions? So the point essentially is this. If you have two impure functions, it's entirely possible that one of the functions depends on state that the other function also uses, or depends on. Think about it this way. If you have a function that reads values from a file and another function that writes values to a file, then depending on which order you do these things, you may have different results. It's pretty possible. But if the functions were pure, then they can't have side effects, which means they can't do things such as write to the file, which means that you can take one thread to run one function there, you can take another thread and run the other function in there, and thus you have parallel execution. So, of course, you can always run anything in parallel, but the point is that when you have pure functions, we're certain that you don't have state that you're taking between the functions. So to finish up with an example, think about this. You've probably also heard of the concept of mathematics. You don't want to dig details of mathematics, so we'll do that in another video. But when you are performing mathematics, you're essentially performing two separate tasks. You're performing math. So math essentially means that you have a function and you run that function over a collection of integers. You are taking the collection of integers and taking type of collection, you pass that as a value to the function. Right? Then you have a collection of the same length with all of the process output, or the process input, i.e. the output. Then you pass those to a reducer that takes the multiple values and constructs a new value from it, which could be a shorter list or a single number or a long. So the interesting part about that reduce is essentially that if your math function is the function that you are running over the input or with the input argument, I should say, if that function is pure, then that means you can parallelize the running of that function. If you have, which is why mathematics obviously have become so popular. So you have a massive data set of millions of rows. It doesn't, of course it matters, but you can still get a very quick execution time because you can parallelize and run it on multiple threads. Just compare that to running it in sequence, which would take massive amounts of time for it. So that's it. I hope you gained a further understanding of why functional programming, or more specifically, pure functions, help us run programs in parallel without running the risk of having one function using the state that another function depends on, which hypothetically or theoretically could cause erroneous output. So that's it, and for more stuff like this, be sure to subscribe. The single responsibility principle, which is standing for the S in the solid design principle, essentially states that a single module or class should be responsible for a single piece of the functionality of the system, which is commonly but the question is then, of course, what is a single thing? Today I want to give you a short explanation which I find very useful. different, but it's slightly different in nuance. So he talks about having a single reason, right? A cause of having to change, instead of the idea that the class or module should do a single thing. So in that sense, Bob Martin talks about what happens to the class in the future, whereas the single responsibility is traditionally stated in terms of what it does currently. I just slightly borrow one of his examples because I think it's very useful in understanding how to sort of slide a pie in what's to be considered a single unit. So he gives an example along something like the following line. Assume that you have a system and think about the different people that can come to your desk and ask you for changes that they want to impose on the system. So think about then what working roles these people have. So if, for example, say it's kind of like an accounting system, it's a bookkeeping system online, right? So you might have a lot of financial reports. So a designer might come to you and ask you to redesign a particular piece of a form, right? So move this entry field here and move this label field here and change the color of this thing and blah, 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 right? But a person from finance might ask you to add completely new fields. For example, might ask you to add a new calculation. Say that there's the law changes and now suddenly all reports need to include such and such a number. So thus they ask you to include that number, right? There are overlaps here, of course, right? In adding the number that the finance guy asks you for, of course, you have to also perform some design. The point is that these are different reasons. It's entirely possible that you add the new finance calculation, you implement the change that the finance person is asking for, and that the designer is completely happy about that, right? But of course, this reasoning is very limited to the idea of work roles and people coming and asking you for changes. But if you're building your own, if you're running your own product, if you're a small startup, or if you for some reason don't actually interact with people who could give you change requirements in such a manner, then you of course have to envision these incoming change requests yourself. You have to say, how would we potentially want to change this in the future? We talk about startup, for example, there's the concept of pivoting, right? So then you would think, how would we potentially want to pivot in the future? If the idea is, for example, we're currently doing this, but potentially we could be doing that, right? That would be a reason to change. Changing from the first thing to the second thing would be a reason to change. So that change needs to be isolated somewhere. But let's generalize a bit. I'm not saying that you always have to think about work role when considering whether you're adhering to this responsibility principle or not. But I find that wording, the wording, a single reason to change, extraordinarily helpful. So think about it from this perspective. Another way to sort of slice the pie would be to say that when something happens in your system, or the order of how things happen, or why something happens, is not necessarily the same thing as how a particular thing happens. Right? So why and when something happens is not necessarily the same thing as what the thing is that happens. So in terms of change, that would mean that it's not necessarily so that the order of the events changes at the same time as the contents of events. Right? I myself currently working on simulation. So the order in which certain events happen in the computer simulation is independent of how they actually happen. Right? So we're simulating ecology, and we have a bunch of animals that we put them into some mental habitat. Animals perform different things such as eating and sleeping and drinking and hunting and whatever. So the order in which we simulate the event could change independent of what those events actually constitute. So I'm using this example, but the point is that has nothing to do with roles, right? Working roles as in a company, but it has everything to do with having different reasons to change. We might, given our domain that we're in, right? Because the things that we're building, the things that we're wanting, it's entirely plausible that we would want to change the order of things without changing the content of the actual thing, and vice versa. So that's all I want to say about Bob Martin's explanation of how
关系 assistant 的一个cái người trợ lý giúp cho mình trong việc viết lách bằng tiếng Anh thì mình thấy là cái này là
So unit testing versus integration testing. What do people mean when they say integration testing? What do people mean when they say unit testing? There are many ambiguous definitions, such as unit testing is something that tests a single unit of work. But again, ambiguous. What does a unit of work mean? Let's talk about that. A unit test is an isolated test. Integration test, on the contrary, is an integrating test. So unit testing is when you're testing in full isolation, not half isolation, but full isolation. And anything that's not completely isolated, by definition, is an integration test because it's not a unit test. So we now have to define what we mean with integrated. A simplified view would be to say that if component, module, class, whatever, uses any other module, component, class, then it's integrated. But that would also, of course, encompass integration with the language or the framework that you're using. When I say framework, I use the term very loosely because I mean framework or library or language or essentially, if you're in Ruby, it's Ruby core. If you're in .NET, it's .NET, etc. So essentially the core of the language that you're currently using. So if you're using file utilities or random or even string helpers such as running regexes, or you have an instance of a string and you say .substring, or you use string interpolation, so formatting or things like this. That would mean that you're integrating with something else. If you take that to its extreme, in absolute, you'll realize that it's very hard to isolate anything if you can't integrate with anything that's given by the language that you are in. So I would take a little bit, a tiny step back from that. Let me give you what I consider to be a fairly unambiguous definition. So I would consider it so. I would say that with the main framework, if it is non-deterministic, then integration. If it's deterministic and in the main framework, I would say that your test is still a unit test. And whenever you are using any piece of code that's not your own, and that's not in the core of the language you're in, or the sort of main framework that you're in, then that makes your test an integration test. However, any code that you write, if your class uses another class, that's necessarily integration always. Doesn't matter if it's deterministic or non-deterministic or anything else. Nothing matters. As long as your class or module uses some other class or module that you wrote, that's necessarily integration. Okay, so that's my quick definition of the difference between unit test and integration test. Pretty sure you were aware that a lot of people are arguing that we should reduce the number of integration tests and have what I say unit tests. But if you think about the definition I've just posed, you will realize that it's kind of tough to isolate fully and turn your integration tests into unit tests. I would subjectively argue that it's worth it, and I won't go in this video into how to actually isolate your integration tests, but I can pretty shortly say that the solution is dependency injection. So if you want to know more about that, subscribe to this channel. Dependency injection, dependency inversion, constructor injection, parameter injection. What does it all mean? Why do we need them? And how do we actually use them? Constructor injection, I find, is one of these things where when you first understand it, you think it's absolutely trivial because you're like, well, I've been injecting values or references through my constructors since like day one. So how is this anything but trivial? But when you then really understand constructor injection, i.e. dependency injection through the constructor, you realize that it's massively powerful. You realize that it's not at all the same thing as just casually passing values through the constructor. There's much more nuance to it than that. So let's first get the concept straight. Dependency inversion is the all-encompassing principle. It states that you should invert the dependencies. So you invert the relationship in a way that might seem unnatural. Dependency injection is the specific act of inverting the dependency. Constructor injection is when you're performing dependency injection through the constructor of an object. And parameter injection is when you're performing dependency injection through the parameter of any function of an object. So stated in the most simple sense I can think of, instead of considering the formal definition, I would think this way. Dependency injection is about never coupling to a concretion, but always coupling to an abstraction, right? Obviously that's an oversimplification because at some point you have to create a concretion, but we'll return to that in the end. So the point of performing dependency injection is that you want to be able to change your instances of classes at runtime and not only at compile time, which essentially means that you can change behavior of your program at runtime and not only at compile time. And which also means that even at compile time you can change the behavior of your program without rewriting classes, but instead by writing new classes and then injecting those members instead of rewriting the old ones. So dependency inversion increases the flexibility of our code. It increases reuse, right? It encourages small classes with limited responsibilities, and it makes it easy to exchange one instance for another instance in order to change particular behaviors. That's one of the aspects. The second aspect is testability. Without dependency inversion, testability or unit testing, isolated unit testing would be really tricky. Because when you want to test in isolation, you want to test a class without integrating with other classes. So in that case, instead of allowing your class to integrate with other classes or allowing your object to interact with other objects, you inject a lock that you have full control of. So you use dependency injection, which is possible because you are designing according to dependency inversion, and inject a class or an object that you have full control over, which means that you can A, test in complete isolation, and B, because of that, avoid unwanted things such as random numbers in your tests, for example. Just imagine if your tests would pass 50% of the time but fail 50% of the time. Totally tricky, you want to avoid that. How do we actually do dependency injection? So I'll only talk about constructor injection because I think when you see how constructor injection works, you'll trivially figure out how parameter injection works. So imagine that you have a class called animal, and imagine then that you have a bunch of animals inheriting from that class. So we have cat, and we have dog, and we have cow, etc. Imagine then that these classes have an instance method called speak. And this instance method doesn't really matter what it does, but let's say it prints some strings. So the cow says moo and the cat says meow and etc. So naively, we might hardcode this behavior of either saying meow or saying moo into the speak method, into the specific classes, i.e. moo would be in the cow class and meow would be in the cat class, etc. This is sort of object orientation 101, right? This is what you learn in class. Of course, in a bigger system, if it's not about saying moo, but it's rather about something very complex, so assume essentially it's a bunch of more code. So then you might think, okay, we put this behavior in a class. So perhaps you have cow speaking behavior, don't speak, and you have cat speaking behavior, don't speak, and so forth. So we now have two hierarchies. We have animals and we have speaking behaviors. Okay, so this is all fine and dandy, but the problem is that we are potentially breaking dependency inversion. Let me explain. So if the cat instantiates the cat speaking behavior and the dog instantiates this dog speaking behavior, and so forth for the cow. Then we are breaking the dependency inversion principle. Because the high-level module, i.e. the cat and the dog and the cow, is coupled to the low-level module, in this case, the speaking module. So dependency inversion says actually you should invert these dependencies such that both the high-level module and the low-level module should both depend on abstractions. The abstractions in this case are the parent classes. So for both of these hierarchies, the parent class for the i.e. animal and the parent class i.e. speaking behavior. Not the concrete speaking behavior nor the concrete animals. So the dependency inversion principle in this case essentially states that animals should not be coupled to concrete types of speaking behavior, but rather to the abstraction. So this means that we want the animal classes to not instantiate their own speaking behavior, but rather that they somehow should receive a speaking behavior and then run the method speak on that speaking behavior. How they would receive that would be through either premature injection or through parameter injection. And the point here is thus that the concrete animal class, i.e. cat, or etc., then only knows about the most abstract, or the abstraction, speaking behavior, and it doesn't know about concrete speaking behaviors such as the cat speaking behavior and the cow speaking behavior, etc. The most interesting point, or the most interesting benefit about this design, I find, is that oftentimes you realize that actually you don't need subtypes. Actually, in many cases, dependency injection is enough, and you don't need inheritance hierarchies, which is probably why people are saying composition over inheritance, right? Because you can compose what behaves as your subtype instead of actually constructing your subtype. In this particular case, assuming animals do nothing else, then cat and dog and cow would all contain the same code. They would just have different names, which makes them completely redundant. So in that case, we only need animal. Thus, this is how we've achieved composition over inheritance, because we only have one animal class, and when we want to construct a cat, we can instantiate a cat speaking behavior and provide it to the animal class, and thus the animal instance will behave as a cat. And similarly for cow and for dog. So if you take the dependency injection sort of to its extreme in absolute, then you will realize that you can always inject dependencies instead of instantiate them. Which is, think about this, also why people say that the new keyword is dangerous. You should always be wary when you see a new keyword. Is that really the correct place to couple to a concretion instead of an abstraction? So using dependency injection, you can always defer using the new keyword. You can always defer instantiating upwards, backwards, out of the system, right? Towards the main of your program. And this is actually what happens if you use dependency injection into madness. Right? In some sense, you could instantiate all of the players in the main of your system and then have no new keywords in the rest of your system. But of course, there are always trade-offs, and I would actually say that a little bit of dependency injection is better than no dependency injection. A little bit of inversion is better than no inversion, which you'll discover when you, for example, try to test movement isolation, or when you try to quickly respond to new requirements without constantly having to change all the code. Thus, dependency inversion, please ask any sort of questions you might have in common, and subscribe to them. Today, I want to entertain the idea that abstraction in object-oriented programming always equals pragmatism from an economical perspective. So usually the argument goes something like this. Because we've got a long backlog of features, we need to ship fast. We can't work with abstraction. We can't work with refactoring because we have features to ship. Another common perspective is startups. Right? Startups that are figuring out what product they're building. So the assumption for discussion is that you think that lean is a good idea. that you embrace the idea